Good afternoon, students. Am I audible? Am I audible, students? Roll number 33, Neha. Am I audible?
Yes, ma'am.
Okay, thank you. We will wait for 2-3 minutes. Let the all participants join. Then we will start. Okay, yes, students. Whether the screen is visible to you? PPTs are visible? Shall I call roll number? Then only you are going to answer me. Roll number 61, Omkar. PPTs are visible?
Yes, ma'am.
Okay. Why the attendance is so less? Only 28 students have joined. Is there any other activity going on? Yes, TY students. Is there any other activities going on? The earlier lecture or practical or any other? Okay, so 30 students have been joined. So let us start with the lecture. So good afternoon, all of you. In the previous lecture, we have started with the second chapter, that is lexical analysis. And in the lexical analysis, we have seen what is the function of lexical analyzer. So basically, lexical analyzer separate out the token from the source program. That is the main objective of it. Along with that, it reports the error. It removes the blank spaces like tab or enter character, new line character, all these, or even space. So all those white spaces are removed with uh, this lexical analyzer. Also, it supports the macro call. So whenever you are using any macro definition, so the variable is getting replaced by the actual value. So we have seen the example of hash define pi 3.14. So the variable pi is replaced with 3.14 in the lexical analysis phase. So that is the very first phase of the compiler, and it performs the token generation. It reports the errors, then it removes the white spaces, and it supports the macro. So these are the four important functions that we have already covered. Then we have seen what are the different errors. So in case of misspelling, we are generating the lexical errors. So lexical errors are nothing but when the token is not getting generated, then it is reported as an error. And it can be handled by using the panic mode error recovery method, in which we can insert a new variable, we can delete a new character, or we can replace the uh, correct character, the incorrect character by correct one, or we can interchange the characters. So these are the error recovery techniques, and it is called as panic mode error recovery. Then we have seen the basic terminologies of lexical analyzer, in which token is the first terminology that we have studied. So token is nothing but the name for a set of input strings with related structure. So we have seen the example of identifier, integer constant. So if I am using ABC or h_1 or calculate, these are all the variables. They are considered as identifiers. So they are following the same rule, and that's why they are named as identifier. So token are different types, like keywords can be there, identifiers can be there, or we can say special symbols can be there, integer variables can be there. So these are number of tokens. Then pattern we have seen. So what is the meaning of pattern? Pattern is nothing but the actual rule. So we have seen regular expressions for the specific pattern. So for identifier, a pattern is the identifier should begin with the alphabet, and it can be followed by any number of alphabets or numbers or special symbols like underscore, @ So all these are considered as the patterns. So a rule which defines the token is nothing but your pattern. Then we have lexeme. So lexeme is nothing but the match in your source program. So identifier is a type of token, but when I write integer a, b, c, so a is found and that a is considered as lexeme, the actual presence of the variable which is matching a pattern. So pattern is matched by variable a and the type of token is identifier. The pattern is the rule associated with the identifier and lexeme is a. So which actually occurs in your source program, that is called as your lexeme. Okay, so these are the terminologies we have seen, and with this example we have got it clear that whenever this is input line given, count is equal to 123, then the tokens generated are for this count, the token generated is identifier. So it is the identifier, the type of the token is identifier. The rule, that is pattern, is the alphabet followed by any number of alphabets or numbers or anything. Then lexeme, the occurrence of the variable itself. So which variable is acting as the identifier is considered as lexeme. Then comes the second token, which is assignment operator. So it has no forms, and that's why rule is equal to and lexeme is also equal to. So they all are same, assignment operator. Then the integer constant has multiple forms because you can have the float numbers, you can have the integer numbers, or it is also known as the integer constant variables. So that is the rule associated with it is digit followed by any combination of digits. So this is the rule or pattern for this. The token is integer constant and the lexeme, which number is actually present in your source program, is your lexeme. So 123 is the lexeme over here. So this part we have seen. Then the attributes of token we have seen. That is nothing but for any particular token, we have a pointer for that lexeme, which is matched. So that is right in this manner in the symbol table. So whenever this example is there, count is equal to 123, then the first is identifier, and you are going to point to the string count. That is nothing but the variable count. Then second is assignment operator, and third is again integer constant. So integer constant, in that again the pointer value is having 123 in it. So that is nothing but the token along with its attribute. Then we have seen the concept of input buffering. Input buffering is the memory area where we are actually reading our source program, because once we read the source program, then only we are going to generate the tokens out of it. So we are having that buffer concept, which is called as input buffer. This input buffer is having two buffers placed side by side, we can say, which is of n bytes, and that's why the concept is called as double buffering. So here we are having the input buffer. So it has two pointers. One pointer is considered as the begin pointer, and the second pointer is considered as forward pointer. So once it encounter any token, then the token is always present between the begin pointer and the forward pointer, right? So that is considered as token, and the entry is made in the symbol table. And once the entry is made, then your begin pointer will move to the next location of the forward pointer and the process continues. Then why there is need of using two buffers, that we have already discussed. That is, we are going to load the contents into each half part so that the processing is carried out in one half part while the loading is going on in the second half part, and which reduces the time required in fetching and loading operation. So that is why we are using the buffer pair. Then in order to check whether the end of first buffer is reached or not, we are having the EOF character that we are knowing it as a sentinel. So earlier this sentinel was not there, and for that we have to check 2 times whether the end of first half is received and whether the end of second half is received. So 2 checks are carried out earlier when we are not making use of sentinels. So whether we are reaching to the first end, then we have to reload the second. So that is the process carried out. And whenever we are reaching to the end of the second, then we have to reload the first half part, as you can read it here. So we are reaching end of first half, then reload the second. If we are reaching at the end of second half part, means here, then you have to reload the first half. So reloading of first half. So these 2 checks are compressed into one. It has 2 tests, end of first half, end of second half. Instead of that, what we can do is we can just simply check whether EOF is reached. So EOF is the special character which is not the part of your source program, and it indicates the end of your first buffer and second buffer. And that is called as sentinel. The sentinel is nothing but your EOF character. And here we are optimizing the common case by reducing the number of tests to 1. So here we are reducing actually the number of tests. Earlier we had 2 tests to check the end of first half part, second half part. Now just we have to check whether EOF is reached. So EOF is available in both the half parts, and that's why just we will check for the EOF. So only one check is carried out. So whenever it is equal to EOF, then loading of first or second half is carried out. Okay. So this much part we have covered in the previous lecture. And now we are going to start with the specifying tokens. The tokens are mainly specified with the help of regular expressions. So you have learned the regular expression in theory of computation, right? So here, generally we are going to have the alphabets only for this language generation, or we can say the regular expression. So how to specify the tokens, that is written over here. For that we need to read the basic terminologies which are used for the generation of the regular expression. So let us read the terminologies. So what is the alphabet? So alphabet is nothing but the finite set of symbols. So we are having A to Z small and capital alphabets with us. So it is nothing but the finite set. Finite means countable. So total 26 alphabets are there. So it is nothing but the finite set of symbols. Here symbols means A to Z, small variables as well as capital variables, A to Z. So that is your alphabet set. Then string. String is nothing but the collection of alphabets. So when alphabets are collected together, then it gives you the string. So what is a string? Basically, it is a finite sequence of alphabet symbols. So we are having the finite again. So it is a finite sequence of alphabet symbols. So alphabets are arranged and a finite group is considered as a string. The next is language. So language is nothing but set of strings. So as simple as that. So such number of strings will, when collected together, they are considered as a language. So here the language is considered as finite or infinite. So that is the main concept over here. Alphabets and strings, they are the finite set, but the language is finite or infinite. Why? Because the language generation is dependent upon the regular expression. For example, alphabet. So what we have seen for alphabet is the set of symbols. So we are having here a small a to z and capital A to Z. So if we consider small a to z and capital A to Z, the 26 plus 26 total 52 symbols are there in this set, which is your finite set. We know the number of elements in this set, and that's why it is called as finite. The second is string. So string is finite sequence of alphabets. So whenever I am writing any string, let us say ABC, then it has the combination of alphabets. That is the one thing. And second thing is its length is known to us. And that's why it is a finite sequence. Is there any difficulty? Roll number A18. Okay. So whenever we are writing any string, it has the finite length. We can count the number of alphabets present in it. What is string? String is the combination of alphabet symbols, and we can definitely count the number of alphabets in it. So it is also a finite sequence. But when I consider a language, the language is referred as set of strings with a particular regular expression. Set of strings with a particular regular expression. For example, if I am having the regular expression as A star, if I am having the regular expression as A star, right? Because it is the formation of the strings by making use of alphabet A. So what are the different elements that I can get with A star? With A star, I can get epsilon, that is the null character, that is 0 occurrences of A. So I will get null. Then 1 occurrence of A, I will get simple A. 2 occurrences, I will get A followed by A. 3 occurrences, I will get A, and so on. As the star indicates multiple occurrences, we cannot predict how many occurrences will be there or what will be the number of elements in this L, because L is your infinite set. L is your infinite set. Okay. Similarly, if I have only A plus B as my regular expression, so what can be the language generated out of it? Language generated is either A or B. So in such example, either A is getting generated or B is getting generated. That is nothing but the language. So in this example, it is the finite set. It has only 2 elements, I know. But for A star, we cannot predict the number of elements, and that's why it is considered as infinite set of strings. Getting it, all of you? So the basic terminologies in the token generation or the specification is: first, alphabet. It is a finite set of symbols. Second is string. String is also a finite sequence of alphabets. And third, language. It can be finite or it can be infinite. It totally depends upon the regular expression that we are using. And ultimately, it is the set of strings. Okay, so these are the basic terminologies that we will be using while specifying the token. So we have dealt with the basic terminologies. Now we will see some operations on the language. So what are the different operations we can carry out on the language that we will see? So the language we have already discussed. It is a finite or infinite set, right? And it is the set of strings, and it is represented with the regular expression. So it has certain operations, or we can perform certain operations on the language. So first operation is union operation. So all of you are aware about these operations. What is union operation? R union S is specified as R or S. So any string X or any variable X where X is belonging to R or X is belonging to S. So that is nothing but the union concept. So it is the combination of all variables present in R with S. So that is nothing but it gives you the combination of all. The next is concatenation. So concatenation plays the and logical and operation between the two languages, we can say. So here R is one language and S is the other language. So when I perform union, then it will contain the elements of R as well as the elements of S. But what happens in the concatenation? Concatenation is R and S. So the AND is carried out, or we can say in short, it is the followed operation. So RS, when I am doing, then X is belonging to R and Y is belonging to S. And when X is getting followed by Y, then it is considered as concatenation. We are connecting two strings, X belonging to R, Y belonging to S. So when this is taking place, that is the X is followed by Y, then it is considered as concatenation. Then clean closure, we have already seen the example of A star. So clean closure is nothing but the R concatenated with itself 0 or more times. So just now we have seen here A star we have taken. So A is concatenated with itself 0 or more times. When A is concatenated with 0 times, then it gives you the null character. When A one occurrence is present, then it will give simple variable or single variable A. When A is concatenating with itself, then it will give you AA and so on. So it is considered as the concatenation with itself 0 or more times. So 0 times means null and more times indicates the further occurrences of A, or here R. So we are having the string like null is there, R is there, RR is there, triple R is there, and so on. So that is nothing but the clean closure operation. So next, some more operations like OR operation, concatenation, we have already seen that. Then how to represent it with the regular expression. So for that, a particular notation is present. So we are having the pattern specification, because earlier we have seen what are the tokens. Tokens are nothing but the symbols that are available in the here. The tokens are nothing but the symbols or set of input strings with related structure. So it is following certain rule, and that's why they are considered as tokens. And that rule or pattern is represented with the help of regular expression. So that is how we are actually representing the regular expression. So the regular expression or the pattern notation is represented like this. So we will read a pattern notation for describing certain kind of set over the strings. So given alphabet sigma, so we always know that sigma is the alphabet set. So it is the concept of theory of computation. Here, empty set, it is a regular expression and it denotes the language with empty or null character. Then for each A belonging to sigma, A is a regular expression. It is very true that regular expression will build itself from null character up to the infinite characters. And that is why we are starting with the first rule that if the regular expression is null, it contains the language in which all null elements are present. Then if single variable A is belonging to sigma and A is a regular expression. So when we write regular expression is equal to A. When we write here regular expression is A only, then what are the language elements present? Only A. Whether null is available over there? No, because regular expression equal to A means only one occurrence of A is described over here. So this regular expression meaning is A is present only one time. And that's why the language specified by it is this. And that is explained over here that for each A belonging to sigma, if A is a regular expression, then it denotes the language as A. Then if R and S are the regular expressions, then the language of R and language of S respectively are given below. So if R and S are the regular expression, so R or S, if it is the regular expression available with you, then you have the language of R union language of S. For example, we will see the example also so that it will be more clear to you. So the first regular expression, I will call it as R, regular expression 1. In short, we are calling it as R, and we will call it as A star, suppose. This is your regular expression 1. And the second regular expression that we will call it as RE2 or S, the second regular expression. So if R and S are the regular expressions, so S is having the regular expression as B star, suppose. Okay. Regular expression 1, that is R is A star, regular expression 2, that is S is equal to B star. So these are the two regular expressions. And when I perform the OR operation between R and S, so R OR with S. So what comes here? Whatever the language associated with R, union the language associated with S. So let us find out the languages associated with R. So can you tell me the languages associated with R or the elements present in the language set? A star, just now we have seen that A star, that is clean closure indicates 0 or more occurrences. So A raised to 0, that is null, then A, then AA, and so on. So it is infinite set. And the language of S, it is B star. So star indicates again 0 or more occurrences. So B is present 0 times means null is there. Then simple B, then BB, and so on. So these are the two language sets respectively for R and S regular expressions. So when I perform the OR between R expression and S expression, so when I perform the OR operation, actually it is making the union of these two language set, and that is denoted over here. So when R or S is specified, it has the combination of all elements from L of R and all elements of L of S. So I will have null, I will have A, then I will have B, I will have AA, I will have BB, and so on. So what I have done, I have performed the OR between, logical OR between these two language sets. And that is why I am getting this result. So when R or S is done, we are actually calculating the union. Similarly, when R followed by S is there, that is concatenation is there, then we are actually concatenating the languages generated by R followed by the language generated by S. So when I am having the R dot S, so what I will do, R followed by S, concatenation you have to do. So null followed by null, I will get null operation first. Then R is getting followed by S. So these elements will be at first. So I will have A followed by B. Similarly, I will have single A followed by double B. It is also possible, and so on. A followed by BB. Because I have to take one element from R, and I will take the second element from S, and I will concate them. Similarly, the first element of R concatenated with second element of S, then also I will get the concatenation as a result. So this is how, when R dot S is specified, that is concatenation is specified, it actually concatenates the language generated by R and language generated by S. And the next is the clean closure. So if clean closure of R is given, then it is same as that of language generated by the R's closure. So it is obvious, if I am considering this language, if I am considering R equal to A star, then the language generated, its star is again the same thing, that is L of R only. So that is R star or R clean closure gives you the language of R closure. Okay, so these are the three operations and their corresponding results in terms of languages. Getting up to this, is there any difficulty? Yes, students. At least you mention in chat box, is there any difficulty? So that we can move to the next point. Okay, so I assume there is no difficulty. You have got, because these are nothing but the revision things we are carrying out. Already you have learned what are the regular expression and what are the different operations on it and how to generate the language. Okay, so common extensions to the regular expression notations. So it is shown in this manner, one or more repetition. It is positive closure, that's why written as R plus. Then a range of characters. So range is specified with a dash. So A to Z. So it indicates A to Z and you need square bracket for them. So it gives you the finite elements which is ranging from small a to small z and capital A to capital Z. Similarly, 0 to 9. So here we are having the range of the characters. The next is the optional expression question mark. So what is the meaning of it? Have you studied the expression question mark earlier? Have you studied in theory of computation? Okay. So here R question mark, what is the language generated by it is the occurrence of R 0 or 1 time. So it has only two elements. 0 occurrences means null and only one element 1 time, that is R. So the optional expression is nothing but 0 or 1 occurrence of the variable. So R is present 0 times and R is present 1 time. So these are the only two language strings generated with R question mark. It is called as optional expression. Then comes any single character. So we are making use of these all things while writing the code for the lexical analyzer. So here dot indicates any single character. So when I say dot star, then it can have the any combination of characters. So dot is nothing but a single character and star means any number of characters. So any single character, let us assume A, B, C, D up to Z or capital A, B, C, D up to Z. So dot is representing that any character. So single character only you have to consider. It also can have the special symbols like less than, equal, less than, greater than signs. All those are considered as the dot. So dot indicates single character. It can be an integer, it can be a variable, that is alphabet, or even it can be a special symbol. Okay, so here it is considered as single character. So we are making use of this in our lexical analyzer generator program. So where I can make use of this, can you think out of the box? Yes. Where I can use that dot character. Which type of regular expression I can generate with that dot character? Any guesses from your side? What dot indicates? Dot indicates any single character. Dot indicates any single character. Or in short, any character, right? So for identifiers, there is a specific rule that alphabet should be at the beginning, followed by any combination of alphabet, number, or special symbols like underscore, at the rate. But how I can check for the preprocessor directive? How I can check for the preprocessor directive? How you are knowing that these are the preprocessor directives? Yes. प्रोग्राम मध्ये तुम्ही जेव्हा सी प्रोग्राम लिहिता तेव्हा तुम्हाला कसं कळतं की हे प्रीप्रोसेसर डिरेक्टिव्ह आहे? येस, हॅश. व्हेरी राईट आन्सर, B68. Very good. So the preprocessor directives are specified with the help of hash, right? we are writing in the program hash include stdio.h, hash include conio.h. So here for this, or even the macro calls like hash define pi equal pi 3.14, right? So here are the different symbols that I'm using. Hash define pi 3.14, or here I am writing hash include stdio. Is there any other method of writing the header files? Here I am writing the angular brackets. Another way of writing the header files is I can use hash include in double inverted comma. I will have conio.h. This will also give you the correct output. Conio.h double inverted comma complete. Okay. So now whenever I'm writing this preprocessor directive, the only thing common is the hash symbol. The only thing which is common is hash symbol, because here in first two lines you are having include, but in the third line you are having define. So there is no match. In the first line you are having the angular brackets. In the second line you are having double inverted. In the third line you don't have any special symbol. Directly you are writing the variable pi and 3.14. Okay. So what you are concentrating on is only the first character hash. Right? So I can have a general rule for the regular expression like this. So when hash is followed by any character, hash पहिल्यांदा आला आणि त्याच्या पुढे काहीही कॅरेक्टर असेल तर मी काय समजते, that are my preprocessor directives. So any character is represented by dot. Just now we are reading this thing. So single character is represented by dot. So when hash is followed by dot, so it is your single character. And when you are having the multiple characters, then I can say star clean closure. So dot star is taking form of include angular brackets stdio.h. Similarly, dot star can take form of include double inverted conio.h, or dot star can take form of define pi 3.14. So it has the capacity to accommodate all those single characters. So I is single character, N is single, C, L, U, D, E, then angular brackets, even double inverted commas, even floating point. All those are considered as your single characters. And that's why the rule is getting generated as when hash is followed by number of single characters. Dot is a single character and star means number of occurrences. So when hash is followed by number of occurrences of a single character, then we are considering this as a preprocessor directive. So I will call it as a preprocessor directive. Getting it? So this is how, by making use of regular expression notations, we are actually forming the patterns to recognize the tokens. So preprocessor directive is a token, and hash followed by dot star is the pattern or the regular expression generated for it. And once this regular expression is generated, we can easily find out the token, because the token is always giving you the special syntax, which is the rule associated with it, right? So this is how we are going to make use of regular expressions to generate the tokens. So let us see some more examples, like for letters. So this we have seen for preprocessor directive. Now for letters, what we can say, small a to z and capital A to z. So and underscore. So if any of these are encountered, then we are going to call them as letters or we are going to call them as strings or identifiers. So all of them gives you the same rule. Next is the digit. So digit is occurrence of 0 to 9. So I am talking about digit of one single length. So we are having 0, 1, 2, 3 up to 9. So single length number is considered as a digit. So this is the rule for digit. Then for identifier, we are having the rule like first is always a letter, that is alphabet. It can be small, it can be capital. And that's why we are having this A to Z, small and capital. So first is a letter followed by any combination of letter or digit or even the underscore. So that is nothing but your identifier's definition. Then integer constant definition काय येईल? Digit plus. So you can have any combination, but as it is an integer constant, you are going to have the at least one integer, and that's why we are not making use of clean closure, but we are making use of positive closure. Okay, so this is how the whole program, for whole program, we are making use of regular expressions or rules to generate the patterns and to find out the tokens ultimately. Okay. So that is about the regular expression and their notations. Okay, so these are the specification of tokens, how to specify the tokens with the help of regular expression that we have learned. Now, how to recognize them? So how to specify them with the help of different rules and operations associated on the regular expressions that we have seen, how to specify the tokens, but how to recognize the tokens, that is our next bit. So recognition of the tokens is done with the help of finite automata. So we have seen in the theory of computation subject. So the regular expressions can be checked, or what we can say is whether they are accepted or not. They are checked with the help of finite automata. Right. So these are the regular languages. So you might have or you might remember this diagram. So very basic thing. The first thing that you have learned in the theory of computation is regular expression. This regular expression is generating the regular languages, and those regular languages can be determined with the help of finite automata. So finite automata, it has two types, DFA and NFA, and both the types recognize the regular languages. Both the types, they recognize the regular languages, right? So that is about the recognition of the tokens is done with the help of finite automata. So let us revise what is the finite automata. The finite automata is the language recognizer which actually recognizes the language. What finite automata is doing, it will check whether the given input string is acceptable or not. Right? Suppose your regular expression is A star. I will take again the example of A star. Then it will generate the regular language, which is null, then single A, then 2 times A, and so on. And suppose the input string given is AAB. Suppose the input string given is AAB. So what this finite automata is doing, it will write that string AAB in your buffer. It will write this string in your buffer, and with the help of this finite control, so it is having the pointer, which is called as finite control, and this is called as language recognizer. So this will decide whether AAB is a part of regular language specified with the regular expression A star. So here is the finite automata we have designed for the expression A star. So for one expression, you have one finite automata associated with it. So it will have the finite automata for A star expression. With respect to this A star, then it will check whether AAB is acceptable or not. So it will check first symbol A, whether A is there in the first position. So it will go further that A is allowed. Then it will read the second character by moving forward. It will again read the second A. So it will check its availability that first A followed by the second A is also part of your regular language or not. So it has encountered yes, that with respect to A star, the language generated is your AA. So AA is also the part of this finite automata, or we can say the regular language. Then again, it will move forward. It will read out this B. Now it will check whether B is the part of this regular language set. So as it is not the part of the regular language set, which is there for A star as the regular expression, so it will identify, that is the language recognizer, it will say it is not acceptable. Meaning is this AAB string is not a part of this regular language set. So what the finite automata will do? Finite automata will give only the two outputs, whether acceptable or not acceptable. That means it will either say no or either it will say yes. So it only recognizes whether the string belongs to that regular expression or not. Okay, so this finite automata is having 5 tuples. Q, that is set of states. Sigma, that are the input variables or input alphabets. Then T is nothing but the transition functions, that is the rules available with us. Then Q0 is initial state and F is your final state. So this finite automata works with 5 tuples. It has 5 tuples, set of states, set of input symbols, set of transitions, then Q0, initial state, and F means final state. Okay. So we are going to have the finite automata, which will check whether, now in the earlier example, the same example for preprocessor directive we will take. So instead of A star, if I am having the preprocessor directive rule for me, that is hash followed by dot star. So it is the rule available. So whenever I am writing the string that hash followed by AAB, BCC, suppose. So this is my input string. So this finite automata will check for this regular expression whether you are generating the proper string or whether the string is belonging to this regular language set or not. So our requirement is what? Only the first symbol should be hash. So it will check for the first symbol. So as it is found that the first symbol is hash and the next all further symbols are any character and their multiple occurrences. So then it will declare that this string is acceptable. So it will return Y, that is acceptable, with this finite control, with this finite automata. Okay. And if hash is not there, suppose the string has only A, B, B, C, C, though it is having this dot star available. Dot star means what? Multiple occurrences of the alphabets. So it is matching with dot star, but as initially this hash is not present, so it will declare that the token is not getting generated as it is not acceptable because hash is not there. So the job of the finite automata is to recognize the token. So this is your input string, which is acting as the what we can say token, and it will decide, the finite automata will decide whether that token is acceptable, yes or no. And if it is yes, then the entry is made in the symbol table. If it is no, then error is generated because the token is not getting generated. Okay, so that is how the finite automata actually recognizes the tokens from this given input strings. Okay, getting up to this? Yes, students. So always remember, specification of the tokens is done with the help of regular expression, and recognition of the tokens is done with the help of finite automata. So for today's lecture, we will stop here. If you have any queries, ask me. Otherwise, today I will take attendance because I'm finding very less number of students are attending today. Only 59 students are there. So I will take attendance today. Just post your attendance in the chat box only once. If you have any query for today, whatever we have discussed today, if you have any query, you can ask. Otherwise, once you write the attendance in the chat box, you may leave. Currently, lecture is also going on. It's okay. I'm about to finish. Okay, all the students, please mention your attendance in the chat box, and those who have written the attendance, they may leave. Thank you.